Good afternoon. This is the catch-up lecture for Chapter 10 for Chemistry 101, Spring 2021. After I get finished with this video, we should be prepared to start Chapter 11 on Friday. That will catch us up to where we should be in the lecture schedule. We left off with talking about all these various functional groups. They have the commonality of having a C-double bond O, a carbonyl group. Start with the first one, it's an aldehyde. Carbon-containing group, C-double bond O, H. The example here we have is acetaldehyde. CH3, so carbon-containing group, C-double bond OH. So here's your aldehyde. Your C-double bond O with two carbon-containing groups is a ketone. The example we have here is acetone, fingernail polish remover. Shown over here. Again, carbonyl, and the carbon of the carbonyl is attached to two carbon-containing groups. We have carboxylic acid, where you have a carbonyl, and attached to the carbon of the carbonyl, you have a carbon-containing group and an OH. The example here is acetic acid, vinegar. So here's your C-double bond O, C-double bond O, OH. The other thing that's attached to your carbon is another carbon-containing group. We have an ester. Again, C-double bond O, carbon-containing group, and then not an OH, but another oxygen carbon-containing group. Carboxylic acid, this is a hydrogen, and the ester, that's a carbon-containing group. The example here, we have methyl acetate. So carbon-containing group, C-double bond O, carbon oxygen, O carbon-containing group. The last example of this particular kind of functional groups is what's known as an amide. C-double bond O, carbon-containing group, carbon nitrogen. Notice we can have other things here than hydrogen. We can have other carbon-containing groups or a bunch of other things. But these are known as amides. This particular example is acetamide. You have your functional groups of your hydrocarbons. All carbon-carbon single bonds, this is an alkane. An example of this is ethane. You have your alkenes, the ENE signals a double bond. Given this generalized structure, the example here is ethylene. You have the YNE, the alkynes, means the carbon-carbon triple bond. The example here is acetylene. Then you have your aromatic compounds, your six-membered carbon-containing rings that have the alternating carbon single and carbon double bonds. The simplest example of this kind of compound is known as benzene. Let's talk a little bit about the physical properties that are present in compounds that contain carbonyl groups. Carbonyl groups are carbon-oxygen double bond functional groups that are present in several different kinds of compounds. So we have functional groups other than oxygen. There are some that do contain oxygen, but other functional groups that are present that don't necessarily involve a carbon double bonded to an oxygen. We have a carbon attached to an alkyl halide. A carbon attached to a halide, fluorine, chlorine, or bromine, or iodine. This is an alkyl halide. The example here is CH3Br. This is methyl bromide. The alcohol. You have an oxygen directly attached to a carbon-containing group. The other atom bonded to your oxygen is your hydrogen. The example here is methanol. We have what is known as an ether group. An ether has two carbon-containing groups to your oxygen. The alcohol only has one. The example of an ether here is dimethyl ether. We can have other functional groups that involve a nitrogen being bonded to a carbonyl group, to a carbon group. Notice no C double bond O here. So this is an amine. Notice no C double bond O. This is not an amide, this is an amine. All these functional groups do not have a C double bond O in them. You will have this chart provided for you for your exam. So you have a carbon group attached to a nitrogen. You can have 2 carbon groups attached to your nitrogen, or you can have 3 carbon groups attached to your nitrogen. They can all be the same. So R3 is the same as R, so whatever R is, it's all the same. We have 3 groups that are identical attached to your nitrogen, or you can have 2 identical groups attached to your nitrogen, or you can only have 1 group attached to your nitrogen. Those are always all defined as amines. Then you can have sulfur directly bonded to your carbon-containing group, and that's known as a thiol. So the simplest example here is a methyl group bonded to your sulfur. So this is methylthionine. So let's get back to compounds that contain different kinds of functional groups. We have carboxylic acids. Contains the combination of two different functional groups, the C double bond O and the OH. You want to write the structure of this. This is a partially expanded structure. Notice the CH3s are not drawn with, the hydrogens are not explicitly expanded out to have lines drawn to it. We're representing that since these hydrogens are to the right of that carbon, these 3 hydrogens are attached to it. This C double bond O is to the right of that carbon, therefore it's bonded to it. Here we have the lines explicitly drawn. If we want to squish that down or squish it down, this CH3 is at the end. This carbon is double bonded to an oxygen and to an OH. Notice this oxygen here is to the right of that carbon. It means that this oxygen is directly attached to that carbon. But what else is that carbon attached to? Well, it's attached to this CH3 and to the OH. So this first oxygen here is represented as the double bonded oxygen. Since there's another hydrogen to the right of this oxygen, the H is written to the right of the oxygen. If we wanted to, we could squoosh this down even more, write CH3CO2H, represented these oxygens are both attached to that carbon. So these are the condensed structures of carboxylic acid. We have aldehydes. If we want to push this down to a condensed structure, the aldehyde is a carbon group bonded to your aldehyde carbon, bonded to a single hydrogen. Carboxylic acid is the OH. The aldehyde is just the H. So we start with CH3, carbon. What's that carbon bonded to? Well, it's bonded to that. So this carbon appears to the right of the methyl carbon. What is this carbon attached to? It's attached to a hydrogen and the oxygen. So we have the hydrogen that's attached to the carbon and this oxygen. No, we write it CHO. Since this hydrogen is attached to the carbon, it appears to the right of it. How many bonds does hydrogen form? It can only form 1. Since it appears immediately to the right of the carbon, it means it's immediately attached to that carbon. The oxygen is to the right of the carbon, means that it's bonded to the carbon. Notice we don't write COH. That would imply, if we wrote CH3COH, it would imply this. That carbon does not have all the bonds, all the valence electrons that it needs. So we write the hydrogen right next to it, implying that the hydrogen is bonded to it. The hydrogen can only form one bond. Since it's immediately to the right of the carbon, it's bonded to the carbon. Oxygen is to the right of the carbon, so it must be bonded to the oxygen, must be bonded to the carbon. How many bonds does oxygen want? 2. So that is why the H comes first, and then the oxygen is to the right of the hydrogen. Ester groups, again, C double bond O, O carbon-containing group. This is an ethyl acetate. The ester group contains the O carbon-containing group directly bonded to the carbonyl group. We walk from this semi-expanded structure to the condensed structure. We've got the CH3. Carbon is attached to 3 hydrogens, which appear to the right of it. This carbon is also attached to the carbon of the carbonyl. Put the double bond O, saying this oxygen is double bonded to that carbon. This oxygen is to the right of that carbon, but this is to the right of that oxygen. So this oxygen here is that guy right there. This oxygen here is that guy right there. So this first oxygen appears immediately to the right of the carbon. It's bonded to 2 things. It happens to be bonded to that carbon twice. This oxygen appears to that carbon. It means it's bonded to it once. The second bond of this oxygen is bonded to that carbon, so CH2, CH3. If we wanted to, we can squish this down even more. Since we have 2 items identical to one another consecutively, we can write it as CO2, CH2, CH3. The very interesting property that carbonyl-containing compounds have is that they generally tend to have positive odors or smells to them. The primary component of perfumes. If you were to get the trade secrets of the perfume industry, which are extraordinarily tightly kept because there was so much profit in it, if you could get the idea and the listing of what the compounds were in a lot of these perfumes, they're esters. But other carbonyl-containing compounds have very positively smelling things unless you have some reaction to them. Benzaldehyde. To some people it smells like cherries or almonds. Isoamyl acetate. Many people says it smells like bananas. Citric acid. Some people say it has an odor to it. You have ethylbutanoate. Some people have said it smells like apples. Some people say it smells like pineapples. So these esters, these things that have the ester functionality, the C double bond O portion of it, have very strong scents to them. To some people, this is very positive, very pleasant smelling things. To other people who have sensitivity to the things, sometimes these things don't smell so good. But primarily, it's the C double bond O functional group that creates part of the aromatic nature of these materials. If we go back to our hydrocarbons, there are what are known as the homologous linear hydrocarbon series. Carbon compounds that are hydrocarbons from C1 to C4. The Lewis structure where we have removed the dots and given the lines for bonds. This is from methane. Here's its condensed structure. Here's the ball and stick model for it. Carbon surrounded by 4 hydrogens. The 2 carbon fragments is known as ethane. That carbon has 4 things attached to it, 3 hydrogens and the carbon to the right. This has 4 things attached to it, the 3 hydrogens and the carbon to the left. The 3 carbon chain system is propane, the gas that you use to barbecue stuff on. So the CH3 here, CH2 attached to the CH3, which is to the right of it, but this CH2 is the right of that CH3, so this carbon has 1, 2, 3, 4 things attached. This carbon has 3 hydrogens and 1 carbon. The ball and stick model is like this. Butane lighters. A 4 carbon fragment. CH3, CH2, CH2, CH3. So we've talked about this. Alkanes are hydrocarbons. Those compounds that have carbon-hydrogen bonds only. Everything is a single bond. Alkanes. They only have carbon-carbon and carbon-hydrogen single bonds. Alkanes that contain chains of carbons but no rings are called acyclic alkanes. These compounds have the general formula C sub N H2N plus 2. So let's do some examples of this to confirm this for you. C2H6, this is ethane. C3H8, propane. C4H10, butane. N is 2. 2 times N is 4 plus 2 is 6. Propane. N is 3. 3 times 2 is 6 plus 2 is 8. In butane, N is 4. 2 times 4 is 8 plus 2 is 10. So these straight chain hydrocarbons have the general formula for them that says carbon sub N, hydrogens 2N plus 2. Acyclic alkanes, these straight chain systems, are called saturated alkanes because they have the maximum number of hydrogens per the carbon atoms. So here we have a 10 carbon system. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Sorry, undecane, 11. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Okay, undecane. This is a saturated system, meaning that at every carbon, whether it's on an end or in a middle carbon, it has the maximum number of hydrogens that can be allowed. So this has 2 hydrogens. It's also bonded to 2 other carbons. That carbon is bonded to 4 things. This carbon bonded to 2 carbons, therefore it can only have 2 hydrogens. That carbon is bonded to 4 things. This carbon bonded to 2 carbons, but it can also be bonded to 2 other hydrogens. All these carbons of this system are saturated. They have the maximum number of hydrogens allowed. Therefore, these straight chains are called saturated. They have all the hydrogens that they can handle. Sometimes the designation of these things is N-butane, meaning normal, meaning CH3, CH2, CH2, CH3. No double bonds, no triple bonds. N-pentane. CH3, CH2, 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 CH3. The N says straight chain, completely saturated. Here are a molecular formula, the name, and the condensed structures of the various hydrocarbon compounds from C1 to C30. 1 carbon is a meth, CH4, methane. 2 carbons has the prefix F, ethane, CH3, CH3. Propane, prop, 3 carbons, C3H8, CH3, CH2, CH3. Bute, 4 carbons, C4H10. CH3, CH2, CH2, CH3. Could we have squeezed these two together? Yes. Pentane, C5. So it's a pent, a pentagon. CH3, CH3, CH2, CH3. Hex, 6. 6 linearly connected carbons, saturated, no double bonds. Heptane, 7 carbons, hept, H-E-P-T, a heptagon. 8, octane, oct, the octagon. The 8, nonane, none, C9. So nonane is a hydrocarbon that has 9 carbons, each having the maximum number of hydrogens attached to them. 10 is decane. You hear the word decade? Okay, 10 years, decane, dec, 10. 11 is undecane, 12 is dodecane, C13 is tridecane. We can go up to 20, which is echeisoane, C21, hene-echeisosane, up to 30, C30, which is triacontane. You're going to need to know from C1 to C10. Meth is 1, F is 2, prop is 3, but is 4, 5 is pent, 6 is hex, 7 is hept, 8 is oct, 9 is known, 10 is dec. Other things, what do you notice about these things? As we go from very simple things to more complicated things, we can see that the boiling point and the melting point of these things start to get larger and larger. Why? Well, right up to about C5, water freezes at about 0 degrees. Oh, no, excuse me. Water freezes at 0. Okay, sorry. Right about pentane, we start to get enough mass present such that the boiling point is not right at the freezing point of water. From C4 to C5, pentane has enough mass to it such that the intermolecular forces are large enough such that it is not a gas at room temperature. Butane, it is a gas at room temperature. There's not enough mass for the intermolecular forces to cause it to be a liquid at room temperature. But pentane, that C5 part, is enough mass that it just is, there's enough intermolecular forces of attraction between the pentane molecules such that it is a liquid at room temperature. Let me see, hexane, boils at 68. Again, now you're increasing the carbon chain. We can get wrapping around of these carbon chains such that the boiling points and the intermolecular forces are sufficient such that these molecules they go to a gas phase at a higher temperature. So as we increase in mass, we see an increase in the boiling point. Again, decreasing intermolecular forces. Again, the wrapping around of the chains. As they get longer, those interactions become stronger, and the ability to wrap around one another becomes stronger. We can have a relationship between compounds that have the same molecular formula, but different connectivity amongst the atoms that are present. So take the formula C5H12. We can arrange those 5 carbons and 12 hydrogens in different ways. We can arrange these 5 carbons such that all 5 are directly connected to one another. 1 at the center and 4 at the periphery. Boiling point of that is 9.5 degrees. We can arrange it such that we take one of these guys, let's just take the vertical one, and we put it at the end of one that's on the periphery. We get this. The boiling point changes radically from 99.5 to 30. If we do one more switch, if we take either one of these away, So we have the completely linear chain. We take this away and put it here. We get to this guy, we get to boiling point of 36 degrees. These are all constitutional isomers of one another. Isomers are compounds that have the same molecular formula, but different atomic connectivity. This carbon is connected to 4 carbon atoms. This carbon atom is connected to 3. This carbon atom is connected to 2. So if we look at these are all the same compound, the same molecular formula, C5H12, but the atomic or molecular connectivity within the molecule is different here than it is here than it is here. These are all different compounds. These have different melting points, different boiling points. These are constitutional isomers. So the connectivity between the carbon atoms amongst all these 3 are different. These are constitutional isomers. When we name these guys, very specific rules. These are what's called IUPAC, International Union of Pure and Applied Chemists. Yeah, big name, big deal. There are three parts to a name for an organic compound. Primarily, we're looking at hydrocarbons, carbon-carbon single bonds, all the way through. You have the base name. How many carbons are in the longest continuous, unbroken, uninterrupted carbon chain? The suffix. What kind of compound is it? Is it an alkane? Straight chain, all carbon-carbon single bonds. Then the ending is ane. If there's a double bond in the molecule, then the ending is ene. If there's a triple bond somewhere in the molecule, the ending is the yne. If it's an alcohol, the ending is ol. If it's a ketone, the ending is one. So there are a bunch of different endings that you can put attached to the base, how many carbons, to further identify what compound this exactly is. Then there's the prefix. This tells what and where things are attached along the carbon chain. So if we take this compound, first thing we do, now we're putting this naming priority system to hydrocarbons. First, you find the longest chain in your molecule. That's your base. So if we count 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6, 1, 2, 3, 1, 2, 3, the longest connection of all those compounds, of all these compounds together gives us a C6 or a hexane. So this is a hexane. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. So either numbering this way or this way, we get 6 carbons. That's the longest chain of carbons that are uninterrupted, connected to one another sequentially. Then we say, okay, do we number from here 1, 2, 3, 4, 5, 6, or from here 1, 2, 3, 4, 5, 6? That depends upon what pieces of spinach or substituents or what do you have hanging off at various positions of carbons along your chain. If we number from this direction to here, we get, this is C1, 2, 3, 4, 5. If we number from 1 to 6, this is position 5. But if we number from this end first, our piece of spinach is at C2. So 5 versus 2. What's smaller? 2. So you number from that end of your longest continuous unbroken carbon chain such that these pieces of spinach have the lowest numbering sequence possible. So we have a piece of spinach, something hanging off our chain at the 2 position. Well, what is it? How many carbon fragment is it? It's a single carbon fragment. That is a meth, single carbon fragment. And to tell us that it's a substituent, a piece of spinach hanging off the main chain, we add the YL ending. So this single carbon fragment is a methyl group. Then we need to list, okay, what is it? It's a methyl group. Where is it? We need to use a number where along that carbon chain, that 6 carbon chain, that single carbon fragment is. So it is at the 2 position. So it's 2-methyl. Where is it? What is it? So we've got a single carbon fragment at the C2 position of a 6 carbon hexane system. So we find the longest carbon chain in the molecule, 6. It's a hexane. We then say, okay, do we have pieces of spinach hanging off of our various carbons? Yes. Therefore, we number from that end of the chain such that that piece of spinach has the lowest numbering possible. Here, it was, if we number this way, it's 5. If we number from this way, it's 2. So that's at the 2 position. What is it? It's a single carbon fragment. Single carbon compound is methane. Since it's a piece of spinach, it's not methane, it's not CH4. It's a single carbon fragment hanging off a chain, it's methyl. The 2 carbon fragment is an ethyl. Eth is 2 carbons. Ethyl says a 2 carbon substituent. 3 carbons is prop. Propol, 3 carbon group. Bute, 4. Butol, 4 carbon group hanging off your chain. There are any number of other kinds of arrangements of carbon-containing fragments. Drive you mad. You're going to need to be familiar with these. There's the isopropyl. Prop, 3 carbons. 1, 2, 3. Iso means that however you count, you cannot count sequentially and get all 3 carbons. One of these carbons of this propyl group is isolated from the other. So you go this way, 1, 2, well, this carbon is not numbered sequentially that way. If you go 1, 2, then that carbon is not numbered sequentially. That is the iso. So it's isopropyl. Butyl. Tert-butyl. Bute, 4 carbons, 1, 2, 3, 4. I guess it's tert because it forms a T of sorts, like that. Carbon, carbon, carbon. Tert-butyl, T-butyl. That's the only way I can explain that. Tertiary butyl. So, name of the substituent. Where is it? What is it? Parent compound. If our compound has more than one piece of spinach, you need to alphabetize them, ignoring any prefixes. Precede the name of each substituent by the position that indicates its location on the chain. There needs to be a number for each substituent. We need to separate the numbers by commas and then separate the numbers from letters by dashes. If we have more than one substituent, let's say we had, make sure I'm not in the blind spot, okay, CH3, CH2, CH3, CH2, 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 CH, CH2, CH3, CH2, 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 CH3. Okay, how many carbons? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Okay, 1, 2, 3, 4. Well, there's more than that there. 1, 2, 3, 4. Nope. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. No, C11. So we're going back and forth, left to right with this, right? This guy. This is an undecane. That tells us that there are 11 carbons in there. The ANE says that all the carbons are connected with a single carbon-carbon bond. Do we have pieces of spinach, carbon fragments hanging off anywhere along our chain? Yeah. We've got a group here and a group there. What are they? They are methyl and they are ethyl. Two carbon fragments, S, YL says substituent. One carbon, meth, YL says it's a piece of spinach hanging off of our ring. Off of our chain. We need to number the chain either left to right or right to left. All I said was that this chain, like right to left, gives us the longest continuous unbroken carbon chain. They're numbered from 1 to 11, but I don't know if this is 1 and this is 11, or this is 1 and this should be 11. We're going to count from left to right and right to left to see which gives us the lowest numbering sequence possible. So let's erase this. These across the top here. CH2, H, CH2, 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 CH, CH2, 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 CH3. Okay, we have 11 carbons. If we start from left to right, so from here this way, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. We have a 3, 7. In this direction, it's a 3, 7. If I go from my right to left this way, with the first piece of spinach we encounter is 1, 2, 3, 4, 5, 6, 7, 8, 9, a 5, 9. What's lower, 3, 7 or 5, 9? 3, 7 is the lower numbering sequence. So we number 1, 2, 3, 4, 5, 6, 7, 8, 10, 11. Okay, so it is a 3, 7 substituted undecane. But what is that 3? A single carbon fragment, a methyl group. So 3 methyl. What is at C7? An ethyl group. Just because the 3 is a lower number than 7 doesn't mean that it's necessarily listed first. We list these alphabetically independent of the number. So what comes first, methyl or ethyl? A, B, C, D, E, F, G, H, I, J, K, L, M, N. So the ethyl comes before methyl. So it is 7-ethyl-3-methyl undecane. We have something at 7. What is it? It's a 2 carbon fragment. We've got something at 3. It's a single carbon fragment. Total number of carbons undecane. So we list them alphabetically. We don't list them numerically, we list them alphabetically. We can also draw cycloalkanes. Carbons, these are where we have, since it's ANE, we have no double bonds amongst these. These are all carbon-carbon single bonds throughout the entire structure. No double bonds whatsoever. The 5 and the 6-membered rings are the most stable for a variety of reasons that you can learn about if you would want to take organic chemistry. I would encourage you to take organic chemistry, but you're not required. So our 5 and 6-membered ring, this 6-membered ring is cyclo, telling us that the carbons are attached in a cyclic system. They come back upon themselves. There are 6 of them. Hex. All the carbon-carbon bonds are single bonds, so it's cyclohexane. This is cyclopentane. Cyclo meaning the carbons are arranged in a cyclic nature such that they come back on themselves. There are 5 of them. Pent. All of them are involved in carbon-carbon single bonds, A and E. Cyclo, the carbons are arranged in a cyclic system. How many? 3. Prop. Ane, all carbon-carbon single bonds. The 4-membered ring system is the cyclobutane. The smaller rings, the 3 and the 4-membered rings, are extraordinarily strained, therefore they're not very stable. When we name cycloalkanes, we basically follow the same procedure that we did with alkanes. We start out with, do we have any piece of spinach hanging off of our ring? Where is it? What is it? Then tell me that it's cyclo. Tell me how many carbons are in the cyclo portion of the ring. Then you tell me, is it A and E for all carbon-carbon single bonds? Is it E and E for carbon-carbon double bonds? Is it Y and E for carbon-carbon triple bonds? You need to tell me that. So we find, if we name this, we start out with the number of carbons in the ring. 1, 2, 3, 4, 5, 6. So this is a cyclo 6, cyclohex. All of the carbons in the ring are a carbon-carbon single bond. So a cyclohexane. Do we have pieces of spinach hanging off various carbons in our ring system? Yes. So you name a number what those pieces of spinach are hanging off your ring. We have 6-membered ring. Cyclohex, all carbon-carbon single bonds, ane. Do we have a piece of spinach hanging off that ring? Yes. Where is it and when is it? So, what is it? It's a single carbon fragment. Methyl, YL, METHYL. Meth is a single carbon fragment. YL says it's a carbon fragment attached to something else. So meth, 1 carbon, YL, methyl, CH3, attached to the cyclohexane ring. If we only have 1 substituent attached to the ring, we automatically define that as the 1 position, because 1 is the lowest position around this ring. So this would be methyl cyclohexane. We don't need to put the 1 because there's only 1 substituent on there. Since we want the lowest numbering possible, we know that that 1 substituent is going to be at the first position, number 1. This system, we have 5 members in the ring. So this is a cyclo, 5 carbons, pent, all carbon-carbon single bonds, ane, cyclopentane. Do we have a piece of spinach hanging off of our ring? Yes. What is it? A 4-membered carbon system. 4 carbons is bute. So this is a piece of spinach hanging off the rings, butyl. We only have 1 group hanging off of our ring. This is at C1, so it's butyl cyclopentane. You don't need to say 1 butyl cyclopentane because we have only 1 position where we have anything hanging off a ring. That is by default the 1 position. So no number is needed for a cycloalkane with a single substituent. For rings with 2 or more substituents, you assign tentatively one of the functional groups as the 1 position. And then you work around the ring to see, relative to that first substituent being 1, where that other substituent falls. So you find out the position with 1 substituent, and then you number around the ring to give the second substituent the lowest number possible. So for the 2, if we have 2 different substituents, we number around the ring to assign the lowest number to the substituents alphabetically. So here in the ring system, you are coordinating numbers with alphabeticity. We have this. How many carbons in the ring? 6. They're arranged in a cyclic system. Cyclohex. All the carbons in the ring are single bonds, cyclohexane. We got pieces of spinach hanging off the ring. Yes. What are they? We've got a 2-carbon fragment at this carbon and a single carbon fragment here. So the 2-carbon fragment is an F. A single carbon fragment is a meth. Since this is a piece of spinach hanging off the ring, it's an ethyl. Since this is a single carbon species and it's hanging off the ring, it's a methyl group. What is listed? Now we need to decide where on the ring are each of the substituents listed, or position-wise. You need to decide which is position-wise. We have an ethyl group here, we have a methyl group. What comes first, E or M? Let me get a color pen that works. What works? What comes first, E or M in our alphabet? E comes first. So your E position is given C1. Now you number around the ring, either counterclockwise or clockwise, that this second substituent has the lowest numbering possible. So if we go around counterclockwise, 1, 2, 3, 4, 5. This would be a 1, 5. If we go clockwise, it's a 1, 3. So 1, 3. If the ethyl is at the here, we go clockwise, we get a 1, 3. 1, 3 is lower than 1, 5, so we number around clockwise. So this is 1, that's 3. So with a cyclic ring system, not with an open chain, with a cyclic system, the alphabetical preference dictates numerical position. It is listed first. So the ethyl at C1, we've got a methyl at C3. So this is 1 ethyl, 3 methyl cyclohexane, not 3 ethyl, 1 methyl cyclohexane. So E comes before M in the alphabet, therefore this is given the 1 position. 1, 2, 3, 3 methyl. So 1 ethyl, 3 methyl. Here are some other examples of some substituted cyclohexane, cycloalkanes. Methylcyclopentane. 5 carbons in the ring, cyclic, so it is cyclopentane, all carbon-carbon single bonds. We have 1 carbon, a single carbon fragment. That's a meth. It's as a substituent. It's a methyl, so methylcyclopentane. Ethyl cyclohexane. If you have more carbons in a carbon chain than you do in the ring, then the ring is listed as a piece of spinach. There are 4 carbons in the ring, but we have 1, 2, 3, 4, 5 carbons in the chain. Therefore, this is named as a substituted 1, 2, 3, 4, 5 hydrocarbon. 1, 2, 3, 4, 5 pentane. Do we have something hanging off of our carbon chain? Yes. What is it? It is a cyclobutyl group. Where is it? C1. So 1 cyclobutyl pentane. Let's try. 5 carbons in the ring. 1 carbon there, 3 carbons there, more in the ring. This is a 5-carbon ring, a cyclopent. All carbon-carbon single bonds, cyclopentane. Do we have pieces of spinach hanging off of our carbon ring? Yes. A single group here, a 3-carbon group here. Single is meth. 3-carbon group is prop. What comes before what? M comes before P in our alphabet. Therefore, this is 1. That's 2. This guy. Again, 5 carbons, cyclopentane. Pieces of spinach, yes. So CH3 is CH2. Methyl, ethyl. Here E comes before M. This is 1. 1, 2, 3 versus 1, 2, 3, 4. So the 1, 3, numbering around clockwise, 1-ethyl, 3-methylcyclopentane. Here we have 1,3-dimethylcyclohexane. That's chapter 10. Hopefully you'll get to watch this. On Friday, we will start chapter 11. Hopefully this was helpful. If you have any questions, need some more examples of things, please make an appointment to stop by my office for office hours, and I will work with you so that you have a better understanding than you currently do. Thank you very much. See you guys on Friday.